Hi everyone. Today we're going to study proposition, truth values, and truth table. Let's begin with the definition of proposition. A proposition is a declarative sentence that is either true or false, but not both. Otherwise, it is called non-proposition. I have here 5 examples. Muscat is the capital of Oman. Number 2, 1 plus 2 equals 10. Third, this sentence is false. Number 4, what a beautiful bird. Number 5, what is your name? The first and second examples are propositions. The first example is true, while the second is false. The third is a paradox, therefore non-proposition. Paradox is a statement that is seemingly contradictory or opposed to common sense, and yet is perhaps true. The fourth and fifth are also non-propositions. The fourth is an exclamation, and the fifth is a question. Let us now define propositional variable. Propositional variable is a small letter alphabet that represents a proposition such as P, Q, R, S, and so on. We have 2 examples here. We assign P to the proposition today is Friday. So we write it like this: P colon and the proposition today is Friday. Another example is the proposition I passed math course. We assign the letter Q for the proposition. So it is written here Q colon I passed math course. Let us now define truth value of a proposition. Truth value of a proposition is true if it is a true proposition and denoted by capital T, while it is false if it is a false proposition and denoted by F. We have here 2 examples. First example is P, the sun rises from the east. This is true. And the other example, proposition Q, the sun rises from the west. And this is false. Now let's go to the truth table. Truth table is a table that represents truth values. This is an example. We have here 2 columns. The first column is for the propositions. So we assign P for the proposition the sun rises in the east. And the proposition Q, the sun rises in the west. The second column is for the truth value of each of the propositions. For the proposition P, we write T because this is true. For the proposition Q, we write F because this is false. Today we're going to study logical operations, namely negation, conjunction, and disjunction. Let's begin with negation operation. Let P be a proposition. We define the negation of P as it is not the case that P. The operation is denoted by minus P and read as not P. The truth value of not P is the opposite of the truth value of P. Therefore, the truth table of the negation operation will be as follows. Here we have two columns. The first column for P, the second column for not P. Considering the first row here, when P is true, not P is false. Second row, when P is false, not P is true. Let's see this example. We have a proposition P. The sun rises in the west. And we know that the truth value of P here is false. So for not P, we will write, it is not the case that the sun rises in the west. Since our P here is false, the not P is now true. When we write not P, we can also write like this. The sun does not rise in the west. Let's have now conjunction operation. Let P and Q be two propositions. We define the conjunction of P and Q denoted by P and Q. We use the symbol inverted V to denote the word and. So this is the proposition P and Q. The table below represents the truth table of the conjunction operation. We have here three columns. The first column for truth values of P, second column for truth values of Q, third column the truth values for P and Q. Let us now consider the first row here. When P is true and Q is true, then P and Q is true. Second line, when P is true and Q is false. So we say P and Q is false. When P is false and Q is true, P and Q is false. When P is false and Q is false, then P and Q is false. The conjunction proposition is always false, except when the truth value for both of P and Q is true. Let's have one example here. Proposition P, it is rainy today. Proposition Q, today is a holiday. When we combine the two propositions here, P and Q, so we write, it is rainy today and today is a holiday. Let's have disjunction operation. Let P and Q be two propositions. We define the disjunction of P and Q denoted by P or Q. the symbol V here is read as OR. So this is the proposition P or Q. The table below represents the truth table of the disjunction operation. Let us consider now the first line. When P is true and Q is true, then P or Q is true. Second, when P is true while Q is false, P or Q is true. When P is false and Q is true, P or Q is true. When P is false while Q is false, then P or Q is false. The disjunction proposition is always true, except when the truth value for both of P and Q is false. Let's have one example. Proposition P, he is walking. Proposition Q, he is talking. When we put together the two propositions, P or Q, so we write here, he is walking or he is talking. Today, we're going to study logical operations. In particular, these are exclusive OR, conditional, and biconditional. Let's begin with exclusive OR operation. Or simply said, this is XOR. Let P and Q be two propositions. We define the exclusive OR of P and Q, denoted by P XOR Q, as the proposition P or Q, but not both. This is the truth table of the XOR operation. Let's begin with the first row. When P is true and Q is true, then P XOR Q is false. Second line, when P is true and Q is false, P XOR Q is true. When P is false and Q is true, P XOR Q is true. When P is false and Q is false, P XOR Q is false. The exclusive OR proposition is true only when exactly one of the propositions is true. Example, the proposition P is A is greater than B. Proposition Q, B is greater than A. The P XOR Q is A is greater than B or B is greater than A, but not both. Let's have now conditional operation, or simply called implication. Let P and Q be two propositions. We define the conditional operation of P and Q, denoted by P arrow Q. We read this as P implies Q. as the proposition if P then Q, or P implies Q. The proposition P is called the hypothesis, and Q is called the conclusion. This is now the truth table of the conditional operation. Let us check the first line. When P is true and Q is true, P implies Q is true. When P is true and Q is false, P implies Q is false. When P is false and Q is true, P implies Q is true. When P is false and Q is false, P implies Q is true. The conditional proposition is always true, except when the hypothesis P is true and the conclusion Q is false. The following four propositions are logically the same and can be interchanged with one another. Number 1, if P then Q. Second, Q when P or Q whenever P. Third, Q is necessary for P. Number 4, P is sufficient for Q. Example 1. Proposition P, you learn discrete mathematics. Proposition Q, you will find a good job. P implies Q, we write, if you learn discrete mathematics, then you will find a good job. Example 2. Proposition P, John is from Chicago. Proposition Q, John is from Illinois. P implies Q, we write, if John is from Chicago, then he is from Illinois. Let's go now to biconditional operation, or simply say, this is by implication. Let P and Q be two propositions. We define the biconditional operation of P and Q, denoted by P if and only if Q. We use the symbol double arrow as the proposition P if and only if Q. This is now the truth table of the biconditional operation. Let us consider the first row. If P is true and Q is true, P if and only if Q is true. Second, when P is true and Q is false, P if and only if Q is false. Third line, when P is false and Q is true, P if and only if Q is false. Next, when P is false and Q is false, P if and only if Q is true. The biconditional proposition is true only when the two of the propositions has the same truth value. Example, proposition P, you can take the flight. Proposition Q, you buy a ticket. P, if and only if Q, we write here, you can take the flight if and only if you buy a ticket. Today we are going to study converse, inverse, and contrapositive of proposition. The converse, inverse, and contrapositive are related to the implication proposition. Given the propositions P and Q, the implication is if P, then Q. In symbol, we write P implies Q. Now the converse, this is given as if Q, then P. In symbol, we write Q implies P. The inverse here is written as if not P, then not Q. In symbol, this is not P implies not Q. The contrapositive is if not Q, then not P. In symbol, not Q implies not P. Let us see example 1. Proposition P, two angles are congruent. Proposition Q, two angles have the same measure. For our implication, we write if two angles are congruent, then they have the same measure. In symbol, this is P implies Q. For the converse, we write if two angles have the same measure, then they are congruent. In symbol, Q implies P. For the inverse, we write here if two angles are not congruent, then they do not have the same measure. In symbol, not P implies not Q. For the contrapositive, we write now if two angles do not have the same measure, then they are not congruent. In symbol, this is not Q implies not P. In this example, since the hypothesis P and conclusion Q are equivalent, all four statements are true. But this will not always be the case. Let us see example 2. Proposition P, it is raining. Proposition Q, the home team wins. For our implication, we write if it is raining, then the home team wins. In symbol, P implies Q. For the converse, we write here if the home team wins, then it is raining. We write in symbol Q implies P. For the inverse, we write if it is not raining, then the home team does not win. In symbol, we write not P implies not Q. And the contrapositive, if the home team does not win, then it is not raining. In symbol, we write not Q implies not P. This is the final answer. Today we're going to study compound proposition and precedence of logical operators. Let us define compound proposition. Compound proposition is a proposition which is a combination of two or more propositions and connected by one or more logic operations. Let's see this example 1. Here we have three propositions. Proposition P, it rains tonight. Proposition Q, I will stay at home. Proposition R, I will read a book. The instruction is translate the logical expression P implies the compound proposition Q and R into verbal expression. The answer is, if it rains tonight, then I will stay at home and read a book. Example 2. Translate the English sentence into a logical expression. You can access the internet from campus only if you are a computer science major or you are not a freshman. For our solution, let us assign the logical values. Proposition A, you can access internet from the campus. Proposition C, you are a computer science major. Proposition F, you are a freshman. The answer is the compound proposition C or not F. This implies A. This is the final answer. Let's see now the precedence of logical operators. Compound proposition can be constructed by using any number of the logical operations. The main important thing is to know the order of the operations in which logical operation in the compound proposition is to be applied first. Last time we studied the operations. These are the negation operation, which is not. This is the symbol for conjunction operation, and we read this as and. The next is the disjunction operation. We read this as or. Followed by the exclusive or operation, or simply said, we say XOR. Next is the implication, and this arrow is read as implies. The last one is the biconditional operation. We read this symbol as if and only if. With this list of operations, this is the same precedence or priority lists that we shall follow. Further, we shall use parentheses to specify the precedence of the operation. Example 1. What is the truth value of A and the compound proposition B or C when A and B are false and C is true? For our solution, let us write again this problem down here. Then let us substitute each of the propositions by its truth value. The A is false, the B is false, and the C is true. Now, because of the parentheses, we shall simplify this operation first, false or true. We know that the truth value for false or true is true. Now, the false and true is false. This is our final answer. Example 2. Determine the truth table of not P or Q. For our solution, let us first write the two columns for P and Q respectively. So we write all the possible combinations of truth values for P and Q. For the P, we have the first two rows to be true, the last two rows to be false. For the Q, we write the alternating true, false, true, false. Next, let us write the third column, that is for not P, based on the given problem. So we will negate the P. So the T here now becomes false, T becomes F, false becomes true, F becomes T. Now for the fourth column, not P or Q. Remember that for the OR operation, it becomes false only when both of the two propositions are false. So T and F is T, F and F is false, T and T is T, F and T is T. This is the final answer. Example 3. Determine the truth value of the compound proposition not P or Q, then and not R. For our solution, let us write three columns for P, Q, and R. Here we need 8 rows for each of the propositions. For the P, we write the first 4 rows to be true, the last 4 rows to be false. For the Q, we have the first 2 rows to be true, second 2 rows to be false, and we follow the same pattern on the last 4 rows. For the R, we write the alternating true, false, and so on. Another column is for not P. So we negate the P. For true here becomes false here. And that is the pattern here. Next, we write the column for not P or Q. In here, this becomes false only when both of the propositions are false. So we have this F and T is T, F and T is T, F and F is F, F and F is F, T and T is T, T and T is T, T and F is T, T and F is T. So we have completed our column here. Next is the not R. We shall negate the R column. So the T becomes F and the F becomes T and the pattern is followed. And the last column is our not P or Q and then and not R. So this column here and this column we will combine with the AND operation. Remember that for the AND, this becomes true only when both of the propositions are true. So T and F is F, T and T is T, F and F is F, F and T is F, T and F is F, T and T is T, T and F is F, T and T is T. This is our final answer. I hope you learned something from this video. See you again next time.